My name is Morgan Mclean. I'm a product manager at Google. In particular, I'm the product manager of our Stackdriver APM software and OpenCensus. For those who aren't aware, our Stackdriver APM software is composed of Stackdriver Trace, Stackdriver Debugger, and Stackdriver Profiler. I'm going to talk about both of those things today, so Stackdriver and OpenCensus. I've actually divided the talk pretty deliberately into two. So we're spending the first half on Stackdriver and the second half on OpenCensus. OpenCensus is an open source project that we collaborate on with a number of other vendors, so I kind of wanted to delineate, put a nice sort of separation between these. A lot of the concepts will be the same, and certainly we'll be doing different demonstrations of both, but just keep that in mind as we go through. The talk is sort of divided in two. So like I said, we're starting with part one, which is about how we actually do observability and optimization and troubleshooting for app development at Google. And this ties into Stackdriver. So I know the term observability is being thrown around a lot at conferences, on the internet, everywhere recently. You can look back at a number of great talks, like certainly one I think that Adrian Cole did a few years ago, called Observability 3 Ways, where he talked about tracing, logs analysis, and metrics. And to be clear, that's a really great way to approach the problem. But I suspect that thinking about observability in terms of the tools that we use to analyze it probably isn't quite as useful as actually talking about the concepts that we want to talk about. And indeed, talking about what we can actually achieve by being able to observe how our application operates. So when we think of Google, at Google observability, we think of actual scenarios that engineers have to adapt to every day. Right? When someone searches for cat pictures, what systems are impacted, or why are some requests slow? Will the system scale if we get a lot more users? And this is where observability, the concepts behind observability give us a lot of, are able to answer these questions that we have. So in practice, we find that observability means a couple things. It means setting expectations. So you would have heard, I think, in this morning's keynote a lot about SLO or SLI monitoring. And that's what we use at Google to actually set expectations for how a service should perform. Right? We set actual sort of standards for the latency given a certain amount of usage should be such. The error budget should be this other thing. And so if you're not able to set those expectations, it becomes difficult when looking at a service's performance to understand if it's operating as it should. The next is context, so understanding what a service actually does. If you're an engineer and you work on a service that's 5 or 10 or even 50 layers down in the stack, you need to understand those interactions all around you. Often that's very difficult, particularly at organizations where they don't have an automated way of understanding how these services are supposed to interact. Right? I'm sure we've all worked in organizations where you might have 5, 10, 20, 50 microservices or more, where you'll have someone who doesn't have that sort of organizational knowledge come in and spend a lot of time just understanding like, oh, I work on this little component of the e-commerce system, but I don't understand how that operates with everything else. And in order to debug problems at scale, you need that context. Next is status. This is probably the most simple out of these concepts. This is just understanding, is my service up? Is it down? How is it performing? What's the resource consumption look like? What's the current latency? And finally, there's one concept that often gets forgotten. That's actually performing root cause analysis. So it's fine to have the first three things, but when you actually have a problem in production, you need to have the tools available to actually solve that problem. It's fine to know that a service is down, and if you follow the other sort of observability concepts and have great tooling to understand like which service is dying, but if you don't have the tools to fix it or understand what in the code is actually broken, you still haven't solved the problem. And so none of this is new, right? This is part of, I think, a broader journey that developers have been on for years, where if you look at client app development, whether that's applications for like desktops or laptops or phones or video game consoles or whatever, there's been a lot of great tools for this for years, right? Think of stack traces whenever you have an unhandled exception running on your Mac or on Windows. Right? Think of local debuggers, local profiling tools. All of these have existed for a long time. Where we've struggled is actually adapting these same techniques to distributed systems development, right? Because it becomes a lot more difficult where you can no longer just attach a debugger to a single system to solve an issue because that might have impacts on other users of that system, and you might not even know which system you need to attach it to. And so that's really the sort of the struggle that a lot of developers have been going through for the last 10 years. As we shift a lot of our computing workloads from client applications up to the cloud or up to running on platforms that you might not even be able to gain much insight into. So that was a bit of a long prologue, but you were promised something about observability at Google, so let's talk about that. So Google runs at pretty extreme scale. Right? That shouldn't be a surprise to anyone. And over the past few decades, we've had to invent new technologies and tools in order to scale and survive. There's a reason that when your internet connection is flaky, people go to google.com to actually see if the internet is up. And if google.com doesn't respond, they tend to assume that just their network connection is flaky. A lot of this is due to our platform and our people, but it's also due to the tools that we have in order to gain insight and be able to fix our systems. So I'm going to start by just giving you a very brief introduction to the services available at Google and the platform. So you've probably heard about things like Borg. Borg is our container scheduling or container orchestration service. This is basically what Kubernetes is based on. And certainly, at Google, you may have heard of things like Stubby. This is effectively an internalized version of gRPC and some other tools. And then storage services like Spanner, Bigtable, and others. The layer that we've talked about a lot less is for our instrumentation and tooling. So for instrumentation, all services at Google are instrumented with something called Census. These are a set of libraries that are baked into Stubby and baked into some of our other technologies that automatically capture traces and app-level metrics for an application. So you'll get distributed traces, much like you would see in Stackdriver Trace, through a backend that we call Dapper, which you can see there. But you'll also get metrics for things like application latency, the queue length of certain RPCs, and so on. And you get this as a developer sort of for free out of the box. You create a new service, Census is already there, it's already capturing this. For profiling, we have tools like Google-wide profiling and pprof that capture information. And we've also got like a production debugger called the Borg debugger. And so we've made a lot of investments in instrumentation to ensure that when you build a service inside of Google, you get all of this automatically for free. You don't have to go reinvent the wheel every time. Indeed, you typically don't even need to add a library. It just works out of the box. It's really nice. For tooling and sort of analysis of this data, we have a number of other backends. So Monarch is where we capture and aggregate stats and analyze them. Dapper, which I mentioned before, is our distributed tracing system. We have pprof for profiling, and like I mentioned before, we have the Borg debugger. And I'm showing you this because in a few minutes we're going to talk about the external story, and we're going to replace a lot of these with technologies and some that you might not. So let's talk about how we walk through a scenario at Google. For example, reducing the latency of an application. So the first step is actually understanding if a service is operating more slowly than expected. So as I mentioned in the beginning, we have SLOs and SLIs, and basically descriptions of a service that tell us how we expect it to operate in production. And so at Google, to launch a service, you need to define those. And so you can set up alerts to find out when your application has breached those barriers. The next is triage. So if you're trying to analyze latency over time, you need to create and store latency metrics for all RPCs. I talked about Census and Monarch and Dapper, and that's how we do that inside of Google. And so that's always running on all services, so you can jump back in time and actually see how your service is performing and how that performance may have degraded or gotten better over time. And then you need to be able to narrow that down and determine the approximate cause of latency. So at Google, you might have requests that hop through tens or even maybe thousands of microservices. The first job is just finding out which layer down the stack is actually slowing things down. Generally, at that scale, it's unlikely that everything has slowed down, though if it has, that's also an interesting development. So you can use tracing to actually find out where it's gotten slow. And finally, you need to go in and solve the problem. This involves actually deploying code or deploying configuration. And so this can be achieved by creating things like custom trace segments and annotations in your traces or logs, or continuously profiling your running code. And I talked about pprof before. That's our solution for that. The other major scenario we see is resolving errors in production. So we talked about latency. Now this is when you actually have some kind of error, whether that's an unhandled exception that's causing sporadic problems for a person, or for some of your users to a total outage. So the first, just like before, is getting notified. And instead of latency budgets, in this case, we have an error budget, right? And so just like those latency, just like SLO or SLI, for errors, we'll fire an alert when those are not met. Then you want to be able to do triage, right? So jumping into metrics analysis, logs analysis, or distributed tracing to find out the source of your error, right? Once again, we're in that scenario where you have tens, hundreds, or thousands of microservices interacting. You need to find out which one or which change to a single service actually caused that problem. And then eventually you want to go and find out the actual code that's causing a problem. Offline debugging at Google is effectively not really an option. You might not be able to reproduce something. It's very difficult to set up a test environment for something that involves like tens or hundreds or thousands of services. That's effectively impossible. And so we needed to invent safe production debugging. And that's the Borg debugger that I mentioned earlier. We finally have one additional scenario, and this is just generally wanting to reduce your costs and optimize code. This is one that you might not hear about as often at other firms. Like you might not be, certainly in my development career, it's not a scenario that came up as often. But for our users, and certainly at Google, when we have all these data centers everywhere chugging away, it's really important that we're able to reduce the cost on those, right? If you think of like being able to reduce your CPU consumption by 1%, 5%, 10% or more at that scale, like this is huge amounts of money that you're saving, and it becomes really, really important the more your business grows. And so when we want to reduce our costs, there's sort of two ways we can go about it. The first is just going through distributed traces and finding services that are heavily impacted by single requests, right? So if it turns out that doing a search to a Google search or maybe checking your Gmail or something goes and hits like tens or thousands of disk spindles or something like that, that might not be the most well-optimized query, right? If you have a single small request that's fanning out across your entire network and grabbing data from various systems and things aren't cached well, that's probably a problem. But the next is actually digging into your service's code. So you can also have situations where a single service is performing poorly, and as a result, you're needing to scale it out a lot more widely than you expected, and we've seen this internally as well as with our customers. And in that case, continuous profiling. So I talked about a little bit about pprof before, but continuously profiling that application, so as an engineer, you can go and look at how the code is actually executing for that app is really powerful. So you can find out if there's some sort of contention going on, or just if you're burning way more CPU cycles on something than you think you should. And so I just want to hit on some of these core concepts again. I apologize just in general if this seems a little vague. We're going to go into a very concrete example in a few minutes. But the core concepts we have here are SLOs and metrics, so actually setting expectations for a service's performance, whether that's latency or errors. Traces and log correlation, so using distributed traces or basically being able to map the context of a request and see how that fans out across services, both to reduce those services' latency or to find out where a problem might be caused. And finally, continuously debugging and profiling an application. Debugging and profiling in production are less common concepts. I'm sure a number of you have heard of distributed tracing before. Certainly, I would expect everyone here knows about distributed metrics and certainly distributed logs. But doing this for profiling and debugging are rather new concepts, and we've got these in a pretty nice demo. And these are things we do at Google every day. So to hit on that point that I opened with, traces, logs, metrics, profiles, everything else, these are not observability. These are the tools that we use to achieve observability. The more of these that you build, the more you're able to actually understand how a series of systems performs in real life, and also you're better able to fix them. Certainly, the term observability will be evolving. Like certainly the 4 or 5 tools that I've introduced here are not going to be the end state that will be in 1 or 2 or 3 years from now. And more will be invented, and that's just going to add to people's ability to observe and debug their running applications. So I've talked a bit about how we do this at Google, and for various reasons, I can't necessarily give you a live demo of the tools we have inside the company. But what I can do is talk about the tools that we make available externally. And as of today, now that we've had some recent launches, those actually map pretty well between what we make available to GCP developers, or really developers anywhere, and what we have inside the company. So that's what I'm going to demonstrate. So before I do that, I gave you this slide before, the tools inside of Google. I'm now going to show you those tools outside of Google. Right, so people here externally are not using things like Borg. You're using Kubernetes, you're using containers running on other container orchestration systems, you're using virtual machines, platform as a service, functions as a service. For our PCs, you're typically using a mix of HTTP, gRPC, maybe sidecars like Envoy, or maybe other RPC systems. For storage, when we talk to customers, they use MySQL, MongoDB, various hosted options, whether that's data store or things from other cloud vendors. For instrumentation, there's been a lot of interesting developments in the space recently. Certainly there's OpenCensus, which we develop, and I'm spending the second half of this talk on, for metrics and traces. But there are also existing systems, right? Like a lot of people here probably are very familiar with using Prometheus for collecting metrics from their applications. And certainly for distributed tracing, like Zipkin is incredibly popular and includes its own client libraries. And so we see clients who are already using those today. For profiling and debugging, those are still a little more unique. These are concepts that I suspect were effectively invented at Google. And so our offerings in this space are relatively unique, but we offer those as well. And finally, for logs, I wrote FluentD here. There's obviously a ton of things in this space. And for tooling, sort of the crux of this talk, we have the tools that we offer. So for metrics, we have Stackdriver monitoring, which people will be pretty familiar with. It was a startup acquired by Google a number of years ago, and it's the brand we use for our monitoring software. We also offer Stackdriver Trace, Profiler, Debugger, Stackdriver Logging, which completes that sort of that list of observability tools that exist at Google, except now they're available to our customers. Just going to skip ahead. So I'm going to skip all the way to the demo. So we have here an application called Hipster Shop. So anyone who went to the keynote this morning would have seen this for the Istio keynote. It's this demo app that we've created to show off various GCP features, and it emulates an e-commerce system. It's written across 8 separate services, I think 3 or 4 of which are written in Go, 2 of which are written in Python, 2 or 3 are written in Node.js, and 1 of them is written in .NET Core. They're all running on Kubernetes. In fact, they're running on GKE. There's no sort of special sauce here. This is using stuff that's been available, for the last year or so. Hipster Shop, this version of Hipster Shop, unlike the one that you saw this morning, is really slow. We did a bit of work to it. We ensured that it takes basically forever to load a page. And even once you load it, when you add an item to your cart, it is unbearably slow. And this is a great example of a web application where if you ship this and told people to go buy stuff here, you'd be losing a ton of your customers right off the bat because it's just so ridiculously slow. And the challenge is it's consistently slow. So if we look at metrics, for example, I think this is the right one. Of course it unloaded. If we look at metrics once they actually load, we will see that, scroll, let's go back to trace. You would have seen that the services were basically consistently slow. Everything is slowed down in this application. So even looking at distributed metrics where you've captured latency from every node of the system, whether it's the catalog service or the front-end service or others, they're all equally slow. And so metrics aren't really going to be able to help you to diagnose what the problem is. So instead, we can jump to Stackdriver Trace. So Stackdriver Trace is a distributed tracing solution. For those who don't know what distributed tracing is, we're able to capture a request as it comes into your first sort of front-end edge services, and then we track that request as it goes to any sub-services as it propagates. So in this case, for example, it hops from the cart endpoint, goes to the currency service, then hops to the cart service, then to recommendations, and then finally several times to the product catalog service, then to shipping, currency, and so on. And so we can see this request as it bounces around the application. We can see 2 things in particular that are probably really bad. The first is it goes to the product catalog service a lot, right? So when we're getting details on a single product, it doesn't really make sense that we would continually call the product catalog database to find out details about that product. That should be cached, or frankly, it's probably just poorly written. It is. Poorly written, and it's just calling it way too many times instead of just keeping the data in memory somewhere. And so, this sounds like sort of maybe a somewhat contrived example, but this is the sort of thing that we see with our customers, and certainly I've seen myself as an engineer, where when you don't have these tools to understand how your application works, when you're not tracking how these requests function, you might not notice that when one engineer was writing something and needed more data from the catalog, they just made another call, right? And this adds up over time, and you get these sort of monstrous webs of application topology in ways that no one expected it to actually function, and that's why you have slowness. But the other even if we had a single call to the product catalog service, most of these are taking well over a second. This one takes basically 1.6 seconds. And so the web application would still be too slow. We're going to dig into the second case. We already know what the problem is in the first case. We know that we need to reduce the number of calls. But the second case is actually the harder one to debug, where the individual calls are really, really slow. And distributed tracing helps a bit. We know that the calls to the catalog are causing the slowdown. That's already taken us through our first level of triage that metrics didn't. But unless you added a ton of custom spans to this trace, you're not going to know why it's slow. And to understand that, we're going to go to Stackdriver Profiler. Stackdriver Profiler is a continuous production profiler. What that means is that it's always running in the background, on and off. So to you as a developer, it's effectively always running. It turns itself on and off at various points to capture profiles. And it has effectively no performance impact. That is also true for trace and debugger. But unlike most production profilers, you can leave this one, you effectively just turn it on, set it, and forget it. You don't have to worry about running it for 15-minute sessions or something like that. You don't have to worry about it slowing down your app. Profiler captures a number of things. Right now we're looking at the heap view, so we're capturing the memory consumption of every function running on this service. We can also look at CPU consumption. We can also look at how threads are interacting. Profiler is great because it runs on all of the instances of your service. So just like trace, just like debugger, you don't have to point it at a particular instance. You don't turn it on a single instance or some kind of canary instance. You simply link it to your code, turn it on, and it's running across all of the instances. And you're going to see performance data captured from all of them. This is the heap view. We don't see anything quite too exciting here. We can look for the get product endpoint, which from the trace was shown to be the slow one, or rather the get product gRPC method, which was shown to be slow from the trace. But this is only consuming 12.5% of the application's total memory, and that's still only about 254 kilobytes. Like, this is clearly not the source of our problems. But when we jump to CPU consumption, just gonna take a swig of my water. When we jump to CPU consumption, we see that things are pretty bad. So this is the get product endpoint. It alone is consuming roughly 93% of this application's CPU, just this one function. Given that I've played around with catalog services code, I know that this shouldn't be the case, right? It has a number of gRPC endpoints, or rather gRPC server methods that handle traffic. It doesn't sort of make sense that get product is using so much CPU. But when we look down on this icicle graph shows consumption on the horizontal axis, and on the vertical axis we're showing how these functions actually call each other. We can see that this calls a method called parse catalog. And parse catalog is effectively consuming the same amount of CPU as its parent function. So this is where all the time is spent. And this is where you're both burning money and burning time. And this seems bad, right? So next we're actually going to jump to the code. This view here is in cloud source repositories, though the code for this application is actually stored on GitHub. The distinction between those is kind of irrelevant for this demo, but we're actually jumping to the code, and we can see we're basically just deserializing a bunch of JSON. So what we've already learned from trace and profiler in a few minutes is that the catalog is slow, or rather, requests to the website are slow. They're slow because the catalog is slow. And the catalog is slow because this parse catalog method is spending all of its time deserializing JSON. And that's probably bad. And so, as a developer, we've learned something that otherwise might be very difficult to understand, or we would only know because we have a lot of existing knowledge of how the system operates. But we've gone through this in a way that a new developer could go through it relatively quickly. And so trace and, in turn, profiler have helped us solve this performance problem quickly and reliably, and we can apply this to other parts of the system. Next, I'm going to show you Stackdriver debugger. In this case, we don't have an error that we've sort of had time to code into the application to debug, so I'm just going to give you a demonstration of debugger and show you why it's useful. So Stackdriver debugger, as I mentioned, is a production debugger. It effectively lets you set breakpoints in production that don't halt customer queries. This is pretty magical. This is one of the things that when we show it off at our booth or at demos like this, we get initially a bit of skepticism from viewers saying, you can't do that, that's not possible. But we can. And so we present everything in this really nice IDE-like interface. It's not wildly different than like Visual Studio Code or IntelliJ or others. And you can click in the gutter and sort of set a thing that looks like a breakpoint. But what we're doing here is setting something that we call a snapshot. And a snapshot is effectively a breakpoint, but we don't halt execution. So execution flows right through it. But we do capture the local variables, and we do capture the stack trace. And just like a traditional debugger, you can use conditions and expressions. I'm not going to demonstrate those today, but it's got basically the same functionality that you would expect when you're debugging something locally on your laptop or on your desktop. And so I'll show that to you right now. We've got a load test running against this application. And so I don't even have to open the app to capture data from it. But if we put a snapshot right here, for example, delete that existing one, we can see how the code executes inside of this convert function. This convert function is inside of the currency service. The currency service will convert in the storefront. The storefront lets you convert from like US dollars to euros to yen, and that's performed by this particular service. Where did it go? There it is. And so the snapshot that we laid down is now being captured at line 123, and we can see the various objects and things that were captured from it. And so, like, for example, if we wanted to see the current, if there was some kind of issue of currency conversion where we thought the wrong rates were being used, and we were looking at the input and everything seemed right, we could actually go in here and jump to the currency conversion rates that are being stored in memory in the service in production right now, right? And so we could very quickly be able to decide if the rates that are being stored are wrong or if there's some other kind of problem occurring. Similarly, we can look at any of the objects here. We can also jump to the call stack and capture the local variables captured in each of those frames. Right, so it's just the exact same power you would expect from a local debugger except it's running live in production and will not affect anything. So it's really, really powerful. We use the same thing at Google with a tool called Borg Debugger that's basically the same thing. It's really, really nice for solving rare production issues. So I'm just going to sort of double click on some of the key benefits that we saw. So Stackdriver debugger snapshots, as well as a feature in debugger called log points that allows you to push out log statements to your application instantly without redeploying it. Remove a ton of deployment steps during root cause analysis. Like today, if you're developing on Kubernetes or some kind of distributed system and you're operating in a production environment where it's either difficult or just impossible to attach a debugger, you would often solve problems like this by adding log statements to your code. Whenever you have some kind of error, you add a bunch of log statements to your code to flush out how it's operating and add things to logs. Redeploy your app with the error still in tow because you don't know what the actual error is caused by. That can take a while. Then you get to read the logs using your logging tool and find out if the system is functioning the way you expect, or maybe get some insight into what the error is. Maybe you found it, maybe you need to add more log statements. And so you go through typically a couple iteration cycles of deploying things to production, which is painful and slow and bad for your customers. With snapshots and then log points, which allow you to just add those log statements if you want the fire hose view, you can do that instantly, which is really, really powerful. And this is why we developed Debugger inside of Google. This is why we use it so often, including some of our biggest teams. Next, we had Stackdriver Profiler. So Profiler operates at extreme scale, but unlike most profilers, and certainly unlike most production profilers, has effectively no performance impact. It's also not limited to analyzing single transactions. It gives you that continuous flame graph view for how your application has been running in production. So it gives you great insight into the amount of CPU used by each function in your code, as well as the amount of heap used, and you can also look at threads and contention and other things like that. And so it gives you a lot of visibility into how your core code is running that you wouldn't have without a tool like Profiler. In particular, the heap view is really useful for detecting things like slow memory leaks. Profiler, in addition to giving you that understanding of how your code operates, is a powerful cost reduction tool. So in the private alpha for Profiler, we had a number of customers come back to us and say with about 1 hour of time, they shaved 10% off their CPU bill, off their compute bill. Depending on your scale, that might just be a small amount of money and something that doesn't really interest you. But once you start running a lot of nodes and your monthly compute bill is fairly high, this is like really tangible money that you can save with a very small amount of time. Additionally, and I'll get into this in a minute, we had some larger customers who were fighting performance problems with some of their services that they were having to scale way beyond what they thought was needed. And with Profiler, they were able to get back to their expected scale by finding, in particular, areas of high CPU consumption that they didn't expect. Finally, I showed you Stackdriver Trace. Tracing is finally becoming a much more popular, much more well-understood thing amongst the development community, which is awesome. But tracing tools tend to either be expensive or difficult to adopt these days. There are certainly open source options. Zipkin and Jaeger are great. But you have to go and manage them yourself and spin up VMs and certainly manage the storage for them, which can be annoying or sometimes expensive. There are also paid options in the space. They also tend to be relatively pricey. Stackdriver Trace is neither of those things. It is simple, easy to get started with, and incredibly cheap. So I mentioned a profiler success story. So Snapchat, it wouldn't be a talk at Next without mentioning Snapchat. Snapchat was one of the alpha customers for Stackdriver Profiler. Along with a couple of other marquee customers, they used it to find some performance issues that they hadn't been able to discover previously. They left us this very nice quote about it being able to pinpoint big consumers of CPU time, and at Snap scale, certainly very large, they were able to both reduce their spend on a number of services and increase their overall performance. So for them, it was incredibly powerful. We had similar stories come from a number of our other alpha clients, as well as certainly now that Profiler's gone to public beta, we've had even more. So that wraps up our whirlwind tour of Stackdriver's APM tools. I didn't do a demo of things like Stackdriver monitoring or Stackdriver's new Kubernetes monitoring tools. There are a number of other talks happening on those, but what I really wanted to show was how the same workflows that we have at Google to both reduce latency of our applications as well as find the causes of errors can be how you can apply those at your own companies. Over the years and in the coming years, we're going to have even more launching in this space. But even today, we've externalized enough of our application tooling or enough of our developer tooling that external developers can effectively go through the same workflows as us, which is awesome. There was one last thing I wanted to touch on. So Stackdriver's APM tools have no limitations on where they can be used. So if you have hybrid cloud applications, things that are running on premises, things that are running on your laptop even, like there's no restriction on where the applications that are being instrumented, where they're running. And so there's no requirement to like only use this on GCP resources. And that's even with the pricing plans. Like, so Stackdriver Profiler, Stackdriver Debugger are currently free. Stackdriver Trace has a pretty generous free tier, and then there's a paid tier above that that's coming into effect in September. But this is all the same regardless of where your applications are running. And we think it's a really competitive offering. Like, if you have stuff that's running just on another cloud, we would love for you to use our tools. It would be awesome. And we think you'll get a lot of value out of it. So I promised this talk would be divided into two parts. The second part is about OpenCensus. So to give you a bit of an introduction, OpenCensus is an instrumentation project that we undertook roughly about 1.5 years ago, maybe 2 years ago. And it's basically, we've been trying to work with other vendors so that we can get better tracing and metrics instrumentation for our tools and for their tools. For those who aren't as familiar with distributed tracing, one of the biggest challenges in this space for vendors, for developers, for everyone else is getting traces to come out of their apps automatically. So I mentioned before that at Google with Dapper, we're able to do this, and it's really powerful, both so it helps us understand how our apps are distributed, as well as debug problems. But we can do that because we're running, a custom version of the JVM. We have our own RPC library, and so we can do a lot of things under the hood to enable this that external developers can't, right? Like, most shops aren't going to go modify the JVM extensively to go do things that they want. They're not going to go build their own RPC system. And so with OpenCensus, we're trying to make this ubiquitous to developers outside the company as it is to Googlers. And to do this, we need to go and build integrations with every single thing that you have that sends and receives an RPC, or anything that really does a slow-running transaction. Right? So where we and other vendors have struggled in the past has been that you need to build integrations across every language for HTTP, other RPC libraries, storage client libraries, things for some kind of slow-running process that runs on each machine, for things like Kafka, for basically any sort of client library, anything you interact with from tens or hundreds of vendors. And it's really slow and really painful to build these. And so we thought, well, that's silly. So with OpenCensus, we've gone together, and I'll have the list of vendors in a minute, but we've actually partnered up with a number of other vendors in the space to go build those integrations so you can automatically get traces and metrics out of your app, and then do some basic analysis on top of those. And so it makes it, as a developer, it makes it really easy to get started with these tools, whether that's with Stackdriver APM, or Stackdriver monitoring, or with other solutions like Datadog or SolarWinds or a number of other partners. So back to the demo app, and we're going to do another demo of OpenCensus, but this is sort of, there's no lines connecting anything, but this is roughly the structure of that hipster shop demo. So it's got a front-end service, email service, currency service, and others. And as I mentioned before, they're written in Go, Python, Node.js, and C#. I listed a database here. The demo that we're using just uses an in-memory data, like just basically just has a big object in memory as its database. But the hipster shop demo, once it's published externally, I think is going to connect to some kind of SQL database. And so just like any other customer application, you have to have integrations for all these things, right? If you want, even if you're just using HTTP and gRPC, you need to go build integrations for HTTP and gRPC across every language, right? If that database there is MongoDB or some kind of SQL database or something else, in order to get traces and metrics from interactions with it, we need to go build those integrations. This is, again, just the problem that OpenCensus is solving. I'm sure a number of you from larger or older companies can attest to, like, you'll have services running in probably 5+ languages, using 10 to 20 different storage technologies that communicate to each other using various different RPC frameworks. Like, the real world out there is a mess. Software is developed over a very long period of time, technologies change, old code doesn't necessarily get deleted. And so in order to make all these things automatic, we need to do a lot of work to actually make traces and metrics show up. So to come back to what OpenCensus is a collection of libraries that we publish on a per language basis to collect traces and metrics. We have support for, and I'll get to the full list in a minute, but we're targeting support for Java, Go, Node, .NET, Ruby, Python, PHP, and C++. So it's a list of 8 languages. The OpenCensus libraries for each language have sort of 3 layers to them. They have the instrumentation layer, so that's the things I was discussing earlier, the automatic plugins for various storage frameworks, RPC frameworks, basically anything you want to capture a trace or metric from. They have APIs, so as a developer, you can manually interact with those. You can create your own custom metrics. You can change the metrics that are being automatically collected. You can add annotations to traces. You can change the trace sampling policy, and so on. And finally, the reason that we've been working with other vendors is this concept of exporters. So exporters are these really small, lightweight pieces of code that allow you to send the data collected by OpenCensus to your backend of choice. One of those backends is Stackdriver. One of those backends is just writing everything out to logs. But you can also send it to backends like Datadog and SolarWinds and Instana and a number of other vendors in this space. And the nice thing about OpenCensus is that the exporters are really small amounts of code. Like if you wanted to support some new backend, you don't have to go re-implement like the tracer and re-implement how sampling works or context propagation for tracing, like any of these really complicated things. You just write a bit of code that translates the data that OpenCensus has in memory to the format you expect and send an RPC to your backend. So it's really, really simple. And our goal of OpenCensus right from the beginning is to include as much functionality out of the box as possible. Right, the scenario we want for most developers is you link an OpenCensus library to your app, traces and metrics come out. That's it. You choose an export, and then traces and metrics come out and get sent to your backend. We don't want developers to be sitting there plumbing things and gluing things together. It's really painful. It means that they're not going to use those tools. And quite frankly, as a company that's in the business of selling more and more distributed systems through technologies like Kubernetes, we want to make this as easy as possible. That's why we invest in OpenCensus. So as I mentioned before, we have support for a number of languages and integrations and exporters. Right now, we have really great support for Java, C++, and Go. For Ruby, Python, and PHP, the tracing is in a production-ready state, and we've been adding support for metrics. Some of those are a little further along than others. And Node.js, I think, just entered an alpha, if I remember correctly, and so Node.js is going to jump to full support pretty quickly, as well as Python. .NET is under development through our partnership with Microsoft. I'll get to that in a minute. But they're going to be handling development of .NET, and I think they also have a pretty strong interest in Python and Node. We have a huge number of integrations, far too many for me to list, and certainly far too many for me to have thrown to this presentation at the last minute. But in general, we support HTTP, gRPC, SQL, SQL clients, MongoDB, most things that you would expect to be there. If you're using OpenCensus and something isn't there that you expect, like you can reach out to us, or certainly we would love if you made a pull request. The whole goal of this project is to get as many integrations right into the main client library so that people can use them out of the box, and so that multiple vendors can rely on and maintain the same set of integrations. Finally, we have exporters for a number of really popular backends. We target our functionality on OpenCensus to always work for our two sort of reference backends for tracing and metrics. So Zipkin and Prometheus support is always there and always guaranteed. We also support Jaeger, SignalFX, Datadog, SolarWinds, Instana, Amazon X-Ray, and of course Stackdriver. More and more backends are being added all the time. With the current architecture of OpenCensus, these exporters have to be implemented on a per language basis. And so some languages might have more support while others don't. At the end of this presentation, I'll talk about a sort of a new project we're working on that's going to expand that support even further. OpenCensus also includes some neat features. So I mentioned analysis earlier. So while it's mostly an instrumentation project, OpenCensus also gives you some very sort of quick ways to understand what's going on in your app. The most prominent of those is something we call Z-pages. So if you read Hacker News a lot, like I do, there was a post 1 or 2 days ago about debugging and how we sort of some of the Borg debugging features used at Google. One of the things that was mentioned there, and all the top-ranked comments talked about, was these sort of Borg status pages or Z pages. And we provide these through OpenCensus to developers around the world. These Z pages are basically small web pages hosted by the OpenCensus client library on each node of your application. It shows basic summaries of any sort of RPCs that have been going through the system, as well as summaries of all the stats on your system. So it basically gives you this little fire hose view for the instance of your app that you're inspecting. It's not necessarily as useful as looking at something like a distributed tracing backend, like Stackdriver Trace, which shows you the end-to-end view. These only show data captured from a single node. But if you think that something's wrong with a particular node, or if your debugging process starts with inspecting a single node, these Z pages are a great place to go find that data. One of the other interesting features we have is our work on the W3C trace context format. So about a year and a half ago, Google and Zipkin started work on this sort of a shared context propagation format for distributed traces. If you're familiar with distributed tracing, you might already be aware of this, but one of the challenges in this space is if you're using different client libraries or different instrumentation frameworks, traces still won't always work together. And so take an example of HTTP. If I have service A, service B, and service C, in order to get a distributed trace, my distributed tracing system has to know that a single request is correlated. And so, you know, and Zipkin uses, for example, the B3 headers that basically set a trace ID for this trace. We started this project with Zipkin, and now a number of other vendors, including Microsoft and others, to basically align everybody onto the same context propagation format. If you're sort of using a single vendor system, this probably doesn't interest you as much, but it's another way that we're able to work better with the community. It's really nice. Finally, a neat thing of OpenCensus is just that you can use multiple exporters at once. So you can send traces and metrics to as many backends as you like. You know, for example, we might have customers who do like some metrics to Prometheus and some go to Stackdriver, right? Or rather, all go to both. But if you're either transitioning between using different vendors or you're at some kind of mixed mode environment where different teams use different systems, which is actually relatively common, OpenCensus will support that. So if, you know, some company gets acquired, comes into your company, they're using a different set of tools. As long as you're using OpenCensus, you can send the telemetry to all of those tools and satisfy everybody, which is really great. All right, so once again, I'm going to hop over to my demo. So inside of this application, we've gone and already added OpenCensus to the services. So I'm going to pull up the code for the product catalog service. There you are. And so we're using OpenCensus in the product catalog service in order to capture traces and metrics. And most of the code is captured here. Like just like I described, this is a really nice scenario where you just basically initialize the OpenCensus service, choose an exporter, and it captures effectively everything you want automatically. In this init tracing function, we register OpenCensus, we tell it to use the Stackdriver exporter, and we tell it to do that for both tracing and stats, and that's about it. I think we also might mention that we're using gRPC. Beyond that, OpenCensus will automatically go and instrument gRPC. It's going to capture application level metrics, so things like latency and packet size, sorry, not packet size, request size and queue length and others, and it's also automatically going to capture distributed traces and propagate context. And we saw that in the Stackdriver trace view. And now I'm going to go try and open the metrics view to show you the example of that. Here we go. I'm just going to zoom out if I can. So these are the metrics captured by OpenCensus. This is inside of Stackdriver. This is not working as I wanted to. And it's going to capture, it's showing us the latency of our application. Here we go, the server latency. And we're going to group this by the different server methods so we can see the latency across each server method. And let's look at the 95th percentile. There we go. Oh, I see the problem. My screen's just too zoomed out. Anyways, I can click on these. If the screen was at higher resolution, you would see the various latencies, 95th percentile latency for each of the different services contained in this application. So it's with 5 or 6 lines of code, I'm now able to get latency metrics from all the different methods handled on this single service. Right? Once I roll this out across all the services in my application, I now get to understand the latency characteristics of every single endpoint attached to every single service, which is really, really nice. And of course, we already saw the traces. But I also mentioned that OpenCensus does custom metrics. And so in addition to automatically capturing these metrics, you as a developer can go and add your own. So what we had added here, I think to the cart service or the checkout service, was the ability to see how many checkout requests are going through the app. And so I've done that here. Let me just pull that up. Apologies for the delay. OpenCensus. Here we go. And so in the code, which I'll show you in a minute, we're capturing the number of items in a cart when the cart is checked out. And we can see the results here. And the code for this was pretty simple. Where on earth is it? Checkout service, there we go. So we've registered the view up above. This is sort of how we create our new metric. And then all we have to do is scroll down to the code where we actually capture it, which is a single line. Here it is. And with this single line of code, in addition to the few that register the view, I've been able to capture a custom metric for my application, and I can send it to the back end of my choice, which is great. Right? You could send this to Prometheus, you can send this to Stackdriver, you can send this to Datadog, wherever you really want it to go, and it's not much work. It's both a great developer experience if you're using a single backend, you can roll this out across your entire application, but it's a great developer, it's an even better developer experience if you're working with multiple backends in a mixed mode environment. And so, like I mentioned before, our goal of OpenCensus is to make as much of this automatic and as easy as possible. And I think with this demo we've achieved that. So I mentioned some really interesting features that are coming to OpenCensus. The first is just more integrations. So today we've got a pretty big list that we're quite proud of, but as time goes on, we want to add the ability to get more traces and metrics automatically from more and more different stacks. So for example, like today, I don't think we support Google PubSub or Kafka. We're going to be adding that. We're going to be adding it for as many technologies as possible. The next that's really interesting is this thing we call the OpenCensus collector service and smarter sampling. So one of the challenges with distributed tracing today is that requests come into your application, they get traced, and typically you sample those at like a 1% rate or something like that. The problem with this is that the average request isn't very interesting, right? If you think of the average request that goes to an e-commerce backend or even to Google, it's probably boring, it sits around the 50th percentile. If you're trying to analyze latency, it's not especially useful. Typically you want to look at requests that are either correlated with errors or requests that are slow, right? In your 95th percentile latency, 99th percentile latency. This is, of course, very challenging because today when you make a sampling decision on a request, you usually do that when it arrives. And when a request comes in, you don't really have a great way of predicting whether it's going to be slow or not. What we're doing, what we plan to do is build this service you can deploy within your application. Traces and metrics from all of your nodes are sent to that service, and then we can make the sampling decision later. And so the sampling decision will be made on this service, and then the traces will be sent to your backend. And so, for example, you could configure it to sample traces that have something like 99th percentile latency, 95th percentile latency, traces for requests that are relatively uncommon, basically traces that are far more interesting. As an application developer, this means you're actually getting actionable data instead of spending all of your time and money on collecting traces that are, frankly, not that useful. And so this is like a big, big thing that OpenCensus is going to provide soon. Next, after that, is providing support for client applications. So one of the challenges of tracing solutions today, or at least some of them, including Stackdriver, is that they don't really give you true end-to-end latency. You can see the latency of an operation that occurs inside of your web application or inside of your data center or inside of Google Cloud, for example. But typically, you're not getting visibility into the actual latency perceived by a client, whether that client is a front-end web application or that client's like an Android or iOS app. And so we're going to be adding support for those in OpenCensus. So we can capture traces all the way from like your user's interaction with some of their software all the way to going to your back end and then back. And so instead of seeing that a user interaction took 200 milliseconds and wondering why your customers say that your app is slow, you can actually see that it's taking 2 seconds because of some kind of network issue between their app, some iOS app and your back-end application. And finally, we of course are looking to expand the list of partners that we work with for OpenCensus. And to that end, this is sort of the big players in the ecosystem. There are a ton of other contributors, typically just open source contributors not working for a particular company. OpenCensus, of course, started at Google. We are the main contributor. We effectively run the project. But in the last few weeks or months, we've also gotten a lot of support from Microsoft, SignalFX, and Pivotal. Pivotal, in particular, right now is maintaining a fork of OpenCensus that basically a .NET copy of OpenCensus Java. And we're there working with Microsoft right now and turning that to an official OpenCensus for .NET library. SignalFX, we've been talking to a lot about co-developing that OpenCensus service, and they've made some other contributions to the library, so we're really excited about that. SolarWinds, Datadog, and Instana have all provided exporters, and with any luck, they'll move up the list and become core contributors. But we're also just really excited to have them involved to any degree. We are always looking to grow the tent for OpenCensus, whether you are a individual open source developer, and there are many, many of them working on the project as well, or you work at another vendor in the space. We're really excited to work with anyone, like really. And so we're really proud of the progress we've made in a fairly short period of time, and attracting some big names of groups that share our vision and want to make tracing and metrics and just generally observability more accessible to everyone. And so hopefully when we show this next year, it will be an even bigger list. All right, I think that's it. Thank you very much for coming. Thank you very much for staying. Yeah.